Few landscapes in the Mediterranean carry a deeper contradiction than Santorini. Whitewashed villages cling to cliffs that plunge into a calm blue sea, while beneath that stillness lies a volcanic system that once unleashed one of the most powerful eruptions known in human history. The island's beauty is inseparable from its violent origin, and the same geological engine that shaped it has not gone quiet. It continues to evolve, to shift, and in subtle ways to reload. How much energy is currently stored beneath the caldera? How does magma move through a system that has already collapsed in the past? And what signals distinguish routine activity from the early stages of something far more significant? Santorini exists because of a long-running tectonic process that defines much of the eastern Mediterranean. The African plate is steadily descending beneath the Eurasian plate at a rate measured in a few centimeters each year, roughly 2 to 3 centimeters annually, equivalent to about 1 inch. This motion forces water-rich oceanic crust deep into the mantle, lowering the melting point of surrounding rock and generating magma. That magma rises through weaknesses in the overlying crust, feeding a chain of volcanoes that form the Hellenic volcanic arc. Santorini is one of the most prominent features of this arc, but it is far from simple. Over hundreds of thousands of years, repeated eruptions built a large volcanic island composed of alternating layers of lava flows and fragmented material such as ash and pumice. Early activity was relatively moderate, producing eruptions that expanded the island outward and upward. Over time, however, the internal structure became more complex. Magma did not simply rise and erupt, it began to accumulate in reservoirs beneath the surface. These reservoirs varied in size and depth, some located several kilometers underground, roughly 3 to 8 kilometers, or about 2 to 5 miles beneath the surface. Each pulse of magma added heat, pressure, and volatile gases to the system. This gradual accumulation set the stage for one of the most significant volcanic events in the late Bronze Age. Around the 17th century, before the Common Era, the system reached a critical threshold. The eruption that followed expelled tens of cubic kilometers of material, estimated at more than 60 cubic kilometers, equivalent to over 14 cubic miles. The eruption column rose tens of kilometers into the atmosphere, exceeding 30 kilometers, or roughly 19 miles. Ash spread across vast distances, settling on islands and coastlines throughout the eastern Mediterranean. As the eruption progressed, the underlying magma chamber emptied rapidly. Without the support of that molten material, the overlying rock collapsed inward, forming the caldera that defines Santorini today. The collapse created a depression several kilometers across, roughly 10 to 12 kilometers in diameter, or about 6 to 7 miles. Seawater flooded into this newly formed basin, triggering violent interactions between water and hot rock. Explosive steam-driven activity followed, amplifying the destructive power of the eruption. The scale of this event left a lasting geological and cultural imprint. Thick deposits of ash buried settlements, preserving structures and artifacts beneath layers that in some places exceeded several meters or more than 10 feet. Evidence of tsunami activity appears in coastal deposits across the Aegean, suggesting that waves generated by the eruption traveled significant distances. These waves were likely produced by a combination of factors, including the collapse of volcanic material into the sea and the rapid displacement of water as the caldera formed. Despite the magnitude of that eruption, it did not represent the end of activity at Santorini. Instead, it marked a transformation. The volcanic system reorganized itself around the newly formed caldera. Over the following millennia, smaller eruptions occurred within the flooded basin, gradually building new land in the form of the Kameni Islands. These eruptions were far less powerful than the caldera-forming event, but demonstrated that magma was still reaching the surface. Modern research has significantly altered the understanding of how this system operates. Earlier models assumed a relatively simple structure, with a single magma chamber feeding eruptions. Current evidence indicates a more distributed network of magma storage zones connected by pathways through the crust. These zones can contain partially molten rock with varying proportions of liquid magma and solid crystals. The presence of multiple reservoirs allows the system to remain active over extended periods without requiring a single large accumulation event. Geophysical imaging techniques, including seismic tomography, have revealed regions of reduced seismic wave velocity beneath Santorini. These regions are interpreted as zones containing molten or partially molten material. One of the largest identified zones lies at depths of several kilometers beneath the caldera floor, extending laterally across a significant portion of the system. Estimates suggest that this zone may contain several cubic kilometers of magma, though much of it is not fully molten. The movement of magma within this network does not always lead directly to an eruption. In many cases, magma intrudes into surrounding rock without reaching the surface. These intrusions can take the form of dikes, which are sheet-like formations that cut through the crust. As magma forces its way into these fractures, it generates earthquakes. These earthquakes often occur in swarms, consisting of many small events clustered in time and space. One such swarm drew considerable attention in early 2025. Beginning in late January, seismic activity increased sharply in the region between Santorini and the nearby island of Amorgos. Over the course of several weeks, thousands of earthquakes were recorded. The total number rose into the tens of thousands, with magnitudes ranging from very small events to moderate ones exceeding magnitude 4. The largest reached approximately magnitude 5.2. This level of sustained activity was unusual for the region. The frequency and distribution of the earthquakes suggested that magma was moving through the crust beneath the seafloor. Analysis indicated the possibility of a dike intrusion extending several kilometers in length. Estimates place the depth of this intrusion at a few kilometers below the surface, roughly 3 to 5 kilometers, or about 2 to 3 miles. Ground deformation measurements supported this interpretation. Instruments capable of detecting minute changes in the Earth's surface recorded subtle uplift and expansion in the area. Satellite-based observations using interferometric radar techniques showed patterns consistent with the injection of magma into the crust. The deformation was measured in centimeters, on the order of a few centimeters, equivalent to about 1 to 2 inches. But even such small changes can indicate significant subsurface movement. Despite these signs, the activity did not culminate in an eruption. The intrusion appeared to stall before reaching the surface. Over time, the frequency of earthquakes decreased and the system returned to a lower level of activity. This outcome highlights an important aspect of volcanic behavior. Not all magma movement results in an eruption. In many cases, the system adjusts internally, redistributing material and relieving pressure without releasing it explosively. The presence of gas within magma plays a critical role in determining how an eruption might unfold. Magma beneath Santorini contains dissolved gases such as water vapor and carbon dioxide. As magma rises, pressure decreases, allowing these gases to come out of solution and form bubbles. If gas accumulates rapidly, it can drive explosive eruptions. The viscosity of the magma also influences this process. More viscous magma traps gas more effectively, increasing the potential for explosive activity. Santorini's magma is typically andesitic to dacitic in composition, meaning it has a relatively high silica content. This composition tends to produce more viscous magma compared to basaltic systems. As a result, eruptions at Santorini often have an explosive character. The Minoan eruption represents an extreme example, but even smaller events can generate ash plumes and pyroclastic flows under the right conditions. Monitoring efforts have expanded significantly in recent decades. A network of seismic stations records ground movement continuously, detecting even very small earthquakes. Global Positioning System receivers measure changes in position with millimeter-scale precision, allowing scientists to track deformation over time. Gas emissions are monitored at fumaroles and hydrothermal vents, providing information about changes in the chemistry of the system. Satellite observations offer a broader view, capturing patterns of deformation and thermal anomalies across the entire caldera. These tools provide a detailed picture of the volcano's behavior, but they also reveal its complexity. Signals can overlap, and interpreting them requires careful analysis. A rise in seismic activity may indicate magma movement, but it can also result from the circulation of hot fluids. Ground deformation can reflect magma intrusion, but it may also be influenced by hydrothermal processes. Distinguishing between these possibilities is essential for assessing risk. The question of whether Santorini is loading toward a major eruption depends on how loading is defined in geological terms. In a strict sense, the accumulation of magma within the system represents a form of loading. However, this process occurs over long timescales. The build-up required for a caldera-forming eruption would likely take thousands to tens of thousands of years. Current observations do not indicate that such a large volume of magma is nearing the surface. What can be observed is a dynamic system that continues to receive magma from depth. Each intrusion adds material to the crust, altering the stress field and potentially creating new pathways for future movement. Over time, these changes can influence how and where eruptions occur. The system does not reset to a static state after each event, it evolves. The caldera itself is a key feature in this evolution. Its presence affects pressure distribution within the crust. The size of the collapsed structure, spanning several kilometers, creates a zone where stresses are concentrated along its edges. These zones can serve as points of weakness where magma is more likely to ascend. The Kameni Islands, located near the center of the caldera, mark one such pathway. Hydrothermal activity within the caldera also provides clues about subsurface conditions. Hot fluids circulate through fractures, heated by underlying magma. These fluids can alter surrounding rock, weakening it and changing its permeability. Over time, this process can modify the structure of the crust, influencing how magma and gases move. The interaction between magma, gas, and hydrothermal systems adds another layer of complexity. Changes in one component can affect the others. For example, an increase in magma supply can raise temperatures, enhancing hydrothermal circulation. This, in turn, can alter gas emissions at the surface. Tracking these interconnections is essential for understanding. The interaction between magma, gas, and hydrothermal systems continues to shape how Santorini behaves beneath the surface, but the broader concern extends beyond internal mechanics to how the system might evolve in the future under changing conditions. Observations collected over recent decades indicate that the volcano is not dormant in any strict sense. Instead, it operates in cycles of quiet accumulation, intermittent disturbance, and occasional surface expression. Understanding where the system currently sits within that cycle remains one of the most critical questions. One of the most revealing indicators of volcanic state is deformation. The ground surface above a magma reservoir can rise or fall depending on whether material is being injected or withdrawn. At Santorini, measurements have shown periods of inflation where the caldera subtly expands outward. During one notable phase in the early 2010s, deformation was recorded over several months, with uplift reaching a few centimeters, roughly 1 to 2 inches. This change corresponded with an estimated addition of millions of cubic meters of magma into a deep reservoir several kilometers below the surface, approximately 4 to 6 kilometers, or about 2.5 to nearly 4 miles. Although that episode did not lead to an eruption, it demonstrated that magma supply into the system is ongoing. Each such pulse contributes incrementally to the overall volume of stored molten material. However, the system also releases pressure through various mechanisms. Small earthquakes, hydrothermal venting, and minor structural adjustments within the crust all act as pressure relief processes. The balance between input and release determines whether stress accumulates or dissipates over time. Another factor influencing volcanic behavior is the mechanical strength of the rocks surrounding the deep magma zones. Over time, repeated heating and fracturing can weaken these rocks, making it easier for magma to move upward. This process does not occur uniformly. Some regions become more permeable, acting as conduits, while others remain relatively strong, temporarily containing pressure. This uneven structure contributes to the unpredictability of magma movement. In addition to ground-based monitoring, the seafloor around Santorini has become an area of increasing focus. Much of the volcanic system extends beneath the Aegean Sea, where direct observation is more challenging. Marine geophysical surveys have identified active fault systems and ancient volcanic centers submerged below the water. These features indicate that volcanic activity is not confined to the visible caldera alone. Instead, the entire region functions as a broader volcanic field. Seafloor mapping has revealed deposits from past underwater eruptions, including layers of fragmented volcanic material spread across the seafloor. These deposits suggest that eruptions have occurred in multiple locations over time, not exclusively within the central caldera. This spatial variability increases the complexity of hazard assessment. An eruption could potentially occur along submerged fractures several kilometers away from the main island, roughly 5 to 10 kilometers or about 3 to 6 miles. Water adds another dimension to volcanic risk. When magma interacts with seawater, it can produce highly explosive reactions. Rapid heating causes water to flash into steam, expanding violently and fragmenting magma into fine particles. This process, known as phreatomagmatic activity, can generate powerful explosions even when magma volume is relatively modest. Such eruptions can produce ash columns, base surges, and ballistic material that travels significant distances. The risk associated with these interactions is not limited to the immediate vicinity. Ash generated by explosive eruptions can be carried by prevailing winds across wide regions. Depending on atmospheric conditions, ash clouds could affect air routes spanning hundreds to thousands of kilometers, potentially reaching parts of southeastern Europe, the eastern Mediterranean, and beyond. Even a relatively moderate eruption could disrupt aviation, infrastructure, and daily life across multiple countries. Tsunami generation remains another major concern. The geological record around Santorini preserves evidence of past wave events linked to volcanic activity. These waves may have been triggered by caldera collapse, pyroclastic flows entering the sea, or submarine landslides. Modern coastal development across the Aegean means that a similar event today would intersect with densely populated shorelines, ports, and tourist destinations. The speed at which such hazards develop varies. Ash clouds can form within minutes of an explosive eruption. Tsunamis generated by sudden events can travel across the Aegean in a matter of tens of minutes to a few hours. This limited response window places emphasis on early detection systems and rapid communication. Monitoring networks are designed not only to detect precursors, but also to provide timely alerts should activity escalate. Long-term risk assessment also considers eruption frequency. Geological studies of Santorini's past indicate that smaller eruptions occur more frequently, often separated by decades to centuries. Larger eruptions, including those capable of significant caldera modification, are far less common, typically spaced by thousands of years. This pattern suggests that while the probability of a near-term catastrophic eruption is low, the likelihood of smaller-scale activity remains meaningful over human timescales. The Khomeini Islands provide a clear record of such activity. Formed through a series of eruptions over the past several centuries, these islands consist of lava domes and flows that emerged within the caldera. Historical eruptions in the early 18th century, mid-19th century, and early 20th century each produced new land and altered the shape of the islands. These events were relatively contained, but still demonstrated the capacity of the system to generate surface activity. Changes in gas emissions also serve as a diagnostic tool. Variations in the output of carbon dioxide, sulfur dioxide, and other gases can indicate shifts in magma state. An increase in deep-sourced gases may suggest that fresh magma is entering the system, while changes in hydrothermal gas composition can reflect alterations in temperature and pressure at shallower levels. Continuous sampling and remote sensing help track these trends over time. Another emerging area of study involves the role of external triggers. Large earthquakes in the surrounding region can alter stress conditions within the crust, potentially influencing volcanic systems. While such interactions are complex and not fully understood, there is evidence that tectonic events can modulate volcanic activity under certain conditions. Santorini's location within an active tectonic boundary means that it is subject to these broader forces. Climate factors also play a subtle role. Changes in sea level, for example, can influence pressure on the submarine portion of the volcanic system. Although these effects are relatively small compared to tectonic forces, they can contribute to long-term trends in stress distribution. Over thousands of years, even minor influences can accumulate, affecting how and where magma moves. The concept of a loaded supervolcano often implies an imminent large-scale eruption, but in geological terms, loading is a gradual and continuous process. At Santorini, the available evidence points to ongoing magma supply, periodic intrusions, and a system that is actively evolving. However, the volume of molten material currently identified does not approach the levels associated with past caldera-forming eruptions. This distinction is critical when interpreting current activity. What remains clear is that Santorini cannot be considered inactive. Its behavior reflects a balance between accumulation and release, shaped by a network of deep reservoirs and pathways. Each new invasion modifies that network, potentially setting the stage for future events. The challenge lies in determining which changes are routine and which signals indicate a transition toward eruption. If you found this breakdown valuable and want more deep, evidence-based coverage of major geological events, make sure to like, share, and subscribe. Tap that hype icon to help this video reach a wider audience and support more detailed updates like this.